Thank you, Mia. It is my pleasure to introduce our good friend, Professor Joe Kracjik, who directs the Create for STEM Institute at Michigan State University. He is a university distinguished professor and a Lepen Philip Professor of Science Education. Throughout his career, he has focused on working with colleagues and science teachers to design and test project-based learning environments to reform science teaching practices to improve the teaching and learning of STEM. He served as the president of the National Association for Research in Science Teaching, NARST, and from which he received the Distinguished Contribution to Science Education through Research Award in 2010. Now, Professor Kracjik has received prestige McGraw Prize for Innovations in Pre-K-12 Education. He has published over 100 peer-reviewed manuscripts and books on project-based learning and science education. So, in 1922, Professor Kracjik received also, as Mia mentioned, an honorary doctoral degree from the University of Tartu in Estonia. Please, Joe.
Thank you so much, Rahel. I'm going to put all my timers on so I can stay at 45 minutes. So what I'm going to speak to you about today is developing student understanding across time. So this has sort of been the driving question, or what's actually propelled me throughout my entire career. I did start off as a high school chemistry teacher for a wonderful 8 years, and then I went into academia. But my driving question has always been, how can I provide my students with the opportunities to learn scientific ideas and habits of minds that they will need to live productive and fruitful lives as global citizens? So I guess that links back to the beginning question from the last session, like what got you involved in the work you did? So that's my driving question that's always propelled me. But what am I going to do today? Today I'm going to describe learning progressions and explain why we need them and discuss why they're important. And hopefully we'll have a good 15 minutes to respond to some questions. So here are some really important basic ideas that I'm going to just start off with. I'm going to use the term knowledge and use proficiency quite a bit. And what do I mean when I say that is that students can really apply, individuals can really apply scientific knowledge and practices to really provide solutions to complex problems or explain real-world phenomena using ideas and practices, and also learn more when needed. So developing usable knowledge is really critical for getting young learners, getting individuals really to try to solve the problems of the future. I do a lot of work internationally, as you might suspect, and one of the things I've noticed as I travel to different countries, including Estonia and Finland, other countries such as Germany and China, that this notion of really trying to support kids in developing knowledge and use is really at the forefront. I recently just finished a project with Thailand, in which one of their organizations brought together teachers from Cambodia, from Kazakhstan, from Vietnam, where they're all thinking about how do we create curriculum materials that can really support our kids in not only developing motivation towards science, but actually developing this usable understanding that's so critical. So I think because of that, I think we're really in an exciting era in science education. But, when we look at our society today, as I just said, we are in an exciting time. Why? Because we do have all these new ideas about how we can really promote student learning, but there's also all these wonderful new ideas in science that we're really uncovering in our world. And of course, as Barbara mentioned, we're also in this really amazing digital era. We've been in a digital era for a long time, but certainly the use of generative AI is also very important. So we're in a very exciting time in our world. but we're also in a very challenging time. And that challenging time results in dwindling natural resources. It's a gorgeous day out there today. I don't think any of us would ever complain. It's not supposed to be, right? This is Estonia, and it is the beginning of March, and typically it's much colder here. So these are concerns, notions of global warming, loss of ecosystems. And one of the things that probably, I didn't put it on the slide, but the lack of belief in science in the last couple of years has really been disturbing. So we're also in a very challenging time. I just want to bring up a little bit what some of my work has revealed. We do know that kids really don't show the kind of deep understanding of scientific ideas that they really need if they're going to solve some of these problems. They, in many respects, don't see the connections between various disciplines. One of the, yesterday we had a presentation on energy, and I'll talk a little bit about energy today as we go on as well. And of course, students don't see the connection between energy in biology, and energy in physics, and energy in chemistry. They always see it as different things, and yet there's only one energy. So we don't, as in our own teaching, we don't make these interconnections. And this is very problematic if we really want to support kids in developing deep understanding. So we do have some work. We've learned a lot. We know a lot. I don't want to sound pessimistic. We know a lot, and we can do a lot. And that's what I'm going to hopefully talk about as we move forward. But I am going to talk about one particular area in which kids really seem to don't really develop much conceptual understanding at all, and yet it's so very important. So what you see in front of you is this graph that's, and I know it's hard to see, I'll explain it. Basically about kids understanding the nature of matter and how matter interacts. And of course, one of the more important aspects about how matter interacts is really understanding what causes things to stick together, the intermolecular forces that really bind things together. And yet, when we interview kids, we find out that they really have very little understanding of what really holds matter together. A lot of kids can mention the octet rule. They can briefly memorize some ideas related to forces and energy, but it's very weak. And you see that trend on the 1, 2, 3, going from left to right, the left black line. Very few students, even in college, because that black line shows undergraduates, don't really understand the nature of forces that hold materials together. Yet it's such an important area. I mean, particularly in this day and age, when we talk about building new molecules. You can't build new molecules and build new materials unless you understand that. And so we have quite a way to go to really try to support kids in this area. Just to show the connections that exist in this room, I first got interested in this area of research when I did my sabbatical, and I got involved with a project with Rahel back in 2005, right? So for all you young folks that are in this room, building these collaborations are so critical because you never know where it's going to go, right? So I got involved in doing this little project with Rahel back in 2005, and of course that interest in what holds things, I always had, as a chemist, I always had this interest in what holds things together, but not necessarily from a research perspective. So it really is an important aspect, building these relationships, that what SciCar is trying to do, because you never really know where you're going to go. That was sort of like a sidewalk from the major talk, but hopefully you followed that. So the question becomes, how should instruction and assessments be designed to promote this kind of integrated, usable understanding that students need? And so in order to answer that question, I'm going to first give you my vision of what is learning and how kids build understanding. And of course, if we're really going to cause learning to occur, we really need to get individuals to make sense out of various ideas and experiences to construct this understanding. And so when ideas can connect to one another, when you can get experiences and ideas, this allows learners to make relationships. And when they have these connected connected relationships, that's when they can actually apply their ideas. Now, I could give a totally different talk that would build off of the wonderful talk we heard by Barbara and Elise this morning about interest, right? I'm not going there. You definitely have to, you're never going to get kids engaged cognitively unless we have them emotionally engaged. That's the premise, right? But we're going to assume we did that. That's a different talk. I can certainly talk about that. This is talking about once kids are there, what happens with building learning. And often I should say that unless we really get them emotionally engaged, they're never going to develop that kind of deep, robust understanding. So here's kind of a visual of what I would mean by kids having thin understanding. They have lots of terms in their head, lots of memorized ideas, but they really don't know how they relate to each other. They have vague ideas. We can go a step further, and this is an example where the kid, a learner, you can see, has made some connections between chemical bonding and electrons, but it's not very sophisticated, really can't use it much at all. And then we can jump up a level, and what we see is a rich network of connected ideas. And what should also be in this particular diagram, which should be the experiences that the kids have actually experienced, which aren't there. But this is what we're after. We're after kids trying to create in their own minds this network of interconnected ideas, because the richer and the more connections learners have, the more likely they're going to be able to apply their ideas in new situations. So this is what we're after. So, how can instruction and assessments be designed to promote integrated understanding across time? So there's no simple solution, but here are some ideas to think about. And I'm going to basically pose 5 ideas for us to think about or ponder, and we'll talk about them. So the first is the learning progressions, and I will explain what a learning progression is for those that you don't know. I'm going to relate that to disciplinary core ideas, talk about the importance of integrating those with scientific practices if indeed we are going to create this thing called usable knowledge. We're going to link that to basic science, as I said, link that to basic scientific ideas, and then we're going to spend a little bit of time talking about curriculum coherence, and then we'll sort of wrap up. So the first idea to ponder is this notion of learning progressions. Well, what is a learning progression? A learning progression is literally a research-based description of how students build their knowledge and gain expertise and sophistication about various ideas across time. And we can think of a learning progression, and I'll show you some examples of them, as being fairly macro, that cover across a number of years, let's say K to 12, or you can also think of learning progressions as micro, within a semester, a much more fine-grained type of learning progression. So learning progressions are actually built upon these 3 important ideas. One is engaging students' prior knowledge. If we don't link into their prior knowledge and their experiences, then it's unlikely they're really going to build the kind of knowledge. We always have to make connections. That will help learners build conceptual frameworks, like the one you saw related to the particle nature of matter, in which there's a lot of nodes richly connected together. And in order to get to that kind of rich conceptual framework, we really have to think about how knowledge builds over time. We're not going to just help kids develop deep understanding of the electrical interactions of matter or of energy or of biological evolution in just one semester. It takes a number of years in order for deep understanding in those areas to develop. So, new understandings are always construction on a foundation of understandings and of prior understanding and experiences, in which learners then need to connect new ideas to the previous ideas in order to construct even further, deeper understanding. And although students are continually introduced to new ideas, unless those ideas are actually connected to previous ideas, learners are not going to develop that kind of integrated, usable knowledge that we like. I like using the analogy, I like using a lot of analogies. One you're going to see a lot today is the staircase, right? Where you can see a building of ideas across time, right? You're at a low level, you build the next level, you build the next level, you build the next level. And like any kind of analogy or model, there's limitations in that vision of that model that you see up there because it's not as straightforward. I wish building knowledge was that straightforward, but it's not. But nevertheless, it gives us an image that we can take a big idea, some understanding, let's say of ecology, let's say of energy, and you can see how even at a very low grade, right, a very young age, as time goes across the x-axis, even at a very young age, we can help kids develop some very important building blocks, building steps that are needed to get to the next step. And if we don't help them go from one step to the next step, if we take out some steps, there's no way to make that next step up because it's too big of a step. That's why I like this analogy, that we have to have the right distance. The kids can constantly build. So building conceptual understandings. Why is building this conceptual framework that we saw of these various ideas connected together, why is that so important? It's important because it guides our solving problems. It guides us in making observation. It helps us in our explaining. And it helps us organize and structure new information. So if we can get a structure built, even in the earliest grades around challenging ideas like energy or evolution, natural selection, we start building those ideas in young grades, then we can always that builds a structure that we can always connect to. If we don't build this structure, then it's going to be hard to actually continue to get more sophistication. So, learning builds over time, and it's a continuous process. But it's not necessarily linear. Right? I'm sure all of us who have been school teachers or faculty members at universities, we've noticed how kids learn one idea and we think they got it and they actually take a little step backwards. So it's never straightforward. And learning these difficult ideas takes time and often come together only as a learner, only as the students work on tasks that force them to synthesize ideas. It's not a memorization process. It's actually trying to connect ideas together by being involved in tasks that make them do something. What's the value of learning progressions? Well, they help guide development of our national standards. If we actually have learning progressions, if we have a sense of how the idea of energy, of ecology, of natural selection builds across time, then it will help us design our standards and what's appropriate at each grade level. That then will help us design curriculum materials, professional learning, and assessments that also can work together to really help kids meet that deep level of understanding. So the second idea to ponder is this notion of disciplinary core ideas. So learning is facilitated when new and existing knowledge is structured around these disciplinary core ideas. There's lots of stuff out there to learn. And as educators, as scientists, as teachers, we actually have to stop and think, what are the most important ideas? What is foundational for every kid having to go forward if they're going to be able to solve some of these major problems that I talked about to begin with? So I like to think of criteria for selecting these disciplinary core ideas. One is that it gives you explanatory power within and across discipline. And so I mentioned some of those ideas. As energy, for instance, is essential to all our disciplines. If we don't understand energy and how energy works, it's hard even to explain why is there so much energy that happens when there's a fierce storm. Where's all that energy coming from? It's hard to imagine, it's hard to understand why, as parents, we worry when the temperature of our children gets so high. So energy is an important interdisciplinary idea. It's not important just to physics, it's important to biology, it's important to geology. So these disciplinary core ideas provide a powerful way of thinking about the world, and when we see something that happens in the world that fascinates us or makes us curious, we have the knowledge, we have the building blocks to try to make sense of that. And so having this foundation of these disciplinary core ideas can help us develop further knowledge in our work. And it's certainly understanding disciplinary ideas is important for intellectual participation as an individual, for new jobs, for et cetera. And certainly going back to my first idea that I mentioned, I think if we help kids understand ideas related to disciplinary core ideas and why we have them, it's going to help people believe more in science than we see today. So what are some contenders of disciplinary idea? Certainly equilibrium. It would be one of them, that things do exist in equilibrium. Biological evolution. The particle theory of matter. I don't think anybody could ever argue with that one. Plate tectonics. Energy. Forces. Ecology. And chemical transformations. So you can think, if you want to, for yourself, if you want to think about what a big idea is, and which I often do in my classes to get kids to think about this, is if you close your eyes and you think of something like energy, like ecology, like plate tectonics, all the ideas that are connected to it give you that big idea. It's not just the term, right? So often when I put this little slide up here, I worry that people are going to think that energy is the big idea. No, not really. The big idea is really if you close your eyes and you see all the connections that are associated with energy. You close your eyes and you see all the associations that are associated with biological evolution. If you close your eyes and you see actually no connections, you probably don't have a very good understanding of that idea, right? So it's a little test for yourself. You should think to yourself, what discipline am I in? What's my big idea? And if you close your eyes and you don't see a lot of connections, probably need to do a little bit more studying. We're going to skip those two slides. So core ideas or disciplinary core ideas really provide a framework for this long-term development. And the reason why they're so important, and I mentioned this already, is that big ideas can be revisited and built upon from early grades in the elementary level to the middle school level to the high school level. I recently just finished a really wonderful study project in which we designed, Barbara was involved in this as well, in which we designed materials for K-5 students, and we did an efficacy study in third grade. One of the third grade standards that we had to help kids meet was to get them to understand that whenever there's a force, there's an equal and opposite force acting on it. If you're going to get it to change directions, change speeds, or stop, right? So that's a really challenging idea. Most high school kids, college kids, don't understand why something stops, why something starts, why something will slow down, why something changes directions. It's a challenging idea. But in fact, in our work, we will get kids at the third grade level to build models to explain those phenomena. Now, if you can do that, if you can say, okay, this is an appropriate idea at the third grade level, and you know your kids at middle school are coming in with that knowledge, just think of how much farther you can take them. And then when they get to high school, you can build on it more. And that's the kind of power that understanding what the core ideas are and realizing that they start at a very young age and we can build on them across time. So learning progressions describe how students progress from less to more sophisticated knowledge in a field and the instructions necessary to achieve that growth. We can have beautiful learning progressions, but unless you have good instruction, good curriculum materials, teachers that know what they're doing, it's not going to work, right? They all work together. So learning progression, so a sequence of successfully more complex ways of thinking about how a disciplinary core idea develops across time. We need to consider how ideas build upon each other to form more complex idea. And critical, this doesn't just happen. It's not developmentally inevitable. It depends upon good instruction and the experience the learners have. So if we're really going to get kids to develop deep knowledge, we really have to have instructional sequence that really can support it. Here's a very generic example of a learning progression going across time. This would be one of those macro level learning progressions. So you start at a very low level, and you're going to progress to a higher level across years. And of course, it really depends upon the instruction that happens in schools. This is an example also of a progression of a core idea across from second grade to 12th grade. And you'll see that at the lowest level, in second grade, third grade, at least in the United States, we expect you can help kids develop a macro model of matter, right? They understand that matter is made up of mass. It's something, right? That mass is not going to disappear. So it's a very macro description of matter. As we get older, as we enter 5th and 6th grade, kids begin to build a particle model of matter in which they can explain phase changes, like what happens to the puddle of water. Why does the water go away? Why is that? It doesn't disappear. It just forms little tiny particles. As we get into the 8th grade level, we're starting to get to a more atomic molecular model in which we can explain the properties and the diversity of matter, of materials based upon particles, molecules. And as we get higher into 12th grade, we begin to really develop a really rich atomic structure model that provides a mechanistic model of why chemical reactions occur. This slide's a little out of place. I apologize. This, for those of you who heard me speak in the past about the next generation of science standards, they are also built upon this notion of a learning progression. But they go a little bit further, which is going to be related to the next topic I'm going to talk about, in that it also integrates practices along with the disciplinary ideas. So when you look at this learning progression, which is also a macro description, it starts again at a very low level, young level, K2, and it builds across time. But it's not only the disciplinary idea that's building across time, it's also the scientific practice. And we'll talk about why that's so important on the next slide. But I did want to point out that there are national standards as well that have started to take up this effort of really trying to think, how do ideas build across time? And in some areas, we have some pretty good knowledge. One of the reasons I picked ideas related to chemistry is because we have some fairly good research based upon that this can actually happen. But the third idea to ponder is the notion of scientific and engineering practices. These are the multiple ways in which knowledge and which scientists go about knowing about the world and exploring the world, and also how engineers go about building things and making things better for us. So, and many of us are very familiar with many of these practices. There are in the U.S., there are some new practices that I've really been trying to push in the U.S., which including kids constructing models. I don't know about you, but from my own learning experience, I never constructed a model myself. I always used someone else's model. I never constructed a model until I was in graduate school. Yet nowadays, we're asking kids in third grades to construct models. But that knowledge construction is really important if we're going to get them to really develop these deep levels of understanding. So these are the various scientific practices. And the reason why I mention them is because understanding of a disciplinary idea is not separable from the context in which we use it. So if we're really going to build understanding, the linking together of both practices and disciplinary ideas is critical. Science isn't just a body of knowledge that is often we represent in classrooms. It's also a process. And it's that linking together of that knowledge and that process which is critical in helping kids really form usable knowledge. And so I like to think of I like to use this example of a rope that you may have heard me speak about before. And the reason why is we can have these different strands of scientific knowledge. We can have our scientific practices. We can have our disciplinary core ideas. We can also have these other really important aspects that every scientist use, which we call cross-cutting concepts. These are ideas like cause and effect, systems that we heard talk about today earlier, structure, function. These are ideas that cut across various disciplines and allow us to look at phenomena in different ways. And of course, so we can have a strand, a rope, that basically relates to each one of these, and we have some power, we have something if we have one of those strands. But one strand is not necessarily strong enough to really solve challenging problems or explain complex phenomena. It's when the three are woven together, are integrated together, that we really get the power to explain challenging and difficult ideas. And so in the curriculum materials that we design in our work, when we think about these learning progressions, like we just saw in what we did in the next generation of science standards, there cannot be a separate treatment of content and inquiry. And that's typically how we always did it in the past. They thought of as separate entities. In fact, if we're going to help kids really learn, these ideas have to be integrated together. So this includes both how we support kids in learning the ideas, but also in how we assess those ideas. So here then is a learning progression that is actually built, or it's a very generic one. It's also very macro, in that it shows about how various ideas and practices would work together and develop across time. So you would see it at a very young age. Kids would have a weak understanding of the practice and the content, and as we build towards, as we go on the year and kids have more experiences, it becomes richer. So I'm going to now give you a fairly fine-grained example of a learning progression. So far you've seen very macro examples. So I'm going to give you a fine-grained example. I'm also going to give you an example of this particular learning progression that blends both disciplinary core ideas and practices together. Now, this example comes from a project that was developed and is used in schools in the U.S. called Interactions. That's the link to the materials. I forgot to mention that you can download these slides. I'll do that at the end of the talk so that you know how to do it. The learning progression work is also built upon the work of one of my grad students, Laura Caldera. And so I'm going to share that work with you. Now, this is Interactions is a curriculum that really focuses on kids understanding why materials stick together, really trying to get at underlying causes, not the memorization of ideas, but the underlying causes of why materials stick together, the forces and the energy that's involved in those situations. Now, I know you can't see this, so I'll talk it through. So what you see is on the left-hand side is where you have the level. So you have a low level, which is a macroscopic understanding, and you get to the top level, which is a microscopic model for energy in this particular case. And this is dealing with electrical interactions. And the ideas that we're looking at is both the types of interactions and the structure and properties of matter in this particular situation. On the right side, the practices that we're really trying to develop is that of using models and constructing evidence-based explanations, and we're working with the cross-cutting concept of cause and effect. And at the lowest level of this learning progression, and we've collected lots of data with students in this idea, we get kids who basically have no mechanistic understanding. This often happens before instructions. So they come in with a macro explanation, no mechanism, and really fuzzy ideas about what causes things to stick together. So that's the bottom level. As we go to the top level, we're getting more mechanistic understanding. Kids can actually put ideas together in causal chains to show why things actually impact each other. And they now are incorporating ideas like forces and fields and charge to explain a variety of different phenomena. So we go from less sophisticated understanding to more sophisticated understanding. This is an example of a learner who basically has very low, this is a level 1 response, so a low level response. So the students were asked to draw a model that explains what happens to the rod and fur when they are rubbed together to cause paper bits to move towards the rod. I think we're all familiar with that kind of experience. And they're supposed to label the drawing. And the interviewer then asks, why do you have to bring the rod close to the paper to cause it to move towards it? And we see in the student response, because static only works when objects are close. So you see they're using just macro descriptions, static. They're not saying why. And when you look at their pictures, you also just see a macro description. They're not getting to the micro level explaining what's going on. And so our goal is to actually, through the interactions curriculum, is actually trying to get them to develop a more microscopic understanding of what happens. That takes us off of the interaction slide. And this goes to some newer work that one of my postdocs is currently involved in. This is the work of Dr. Pong He, who unfortunately is leaving Crate and will be going to Washington State University. But, that's the whole purpose of bringing in good postdocs. You want them to leave, unfortunately. Pong has done some really wonderful ideas, wonderful work with learning progressions. And the reason why is that he's not only considering how the disciplinary idea and the scientific and engineering practice and the cross-cutting concept develop across time, he's recognizing that with any group of students, some students are going to take different pathways. And so often when you think of a learning progression, it's not necessarily that you're going to have a linear progression. Sometimes you can have different pathways. And so Pong's work, as you can sort of see in this diagram, I know it's hard to see, Pong's work in this particular case really shows how you move students from understanding ideas around understanding that characteristic properties can explain materials, right? Goes from the low level, that's that one. And there can be different pathways to get to the top level in which you're explaining why a chemical reaction occurs. And that's a really important way of thinking about learning progression. It's very different in the past. The learning progressions that have been produced have always been fairly linear. And Pong's notion of these multiple pathways, I think, is really critical. And actually, if you want to learn more about Pong's work, he will be presenting at NARST if you're going to be going to NARST, or you can write us and can certainly share papers with you. So how should instruction and assessment be designed to promote integrated understanding across time? There's really no simple solution. I wish there was. But we do need to design instruction and assessments with respect to learning progressions, and we really need to think about how these core ideas and scientific practices and cross-cutting concepts actually work together to develop the kind of understanding we want. And of course, one of the reasons why looking at learning progressions and these ideas work together is this notion of curriculum coherence. If we really hope to see kids leave our classrooms, then we really need to develop curriculum that's coherent both within a unit, right? So you can have coherence within a unit, which is really valuable, but you also need to have coherence across units, and then you need to have coherence across years. And if we can get this idea of actually ideas being aligned with each other, but getting kids to use that idea at deeper and deeper levels at each time period, this is how we're going to really develop this really rich understanding. So the notion of coherence really responds nicely with the idea of learning progressions. When you look at my slides, you can look at some strategies. Just a little brief on some concluding remarks, what I've brought up to now. Work's not done. I'll talk about some possible research aspects in a second. We do really need to conduct more research in this area. It is a fledgling area. Interesting enough, I just finished a book that's going to be released next year on learning progressions. It's a series of researchers throughout the world with chapters in that book. I've done this with two of my colleagues. So hopefully that'll be out soon. But we need to do more to develop and test learning progressions. And really to identify, in order to do that, we really need to identify, first of all, what are the important ideas that we want to really understand. We need to describe their levels. We need to test those levels out if they're really correct in classrooms. Then we can create learning progressions or learning performances, and based upon that, we can design curriculum materials. And of course, all this really has to be tested in classrooms. But briefly, this is some potential areas of research that I think is really needed. We really need to investigate learning progressions across disciplines and grade levels. So right now, a lot of the learning progressions that have been designed are pretty much related to just a discipline. And we really need to focus more on how we can be more interdisciplinary in our learning progression work. Further research on developing and validating learning progressions that integrate the three dimensions of scientific knowledge also really needs to occur. That we only have a few examples of those. Most of the ideas of learning progressions that are out there are simply just focusing on core ideas, but there is now a body of knowledge that basically says if we're really going to support kids, it just isn't the core idea. It really is the core idea working together with the disciplinary ideas. So we need to conduct more design-based research that can really track students' learning across time. This is very challenging work, involves both qualitative and quantitative aspects of our work. So researchers really need to start using curriculum materials, assessments, and professional learning purposefully and principally designed to foster student learning across these big ideas. So here's just a quick summary of some of the big ideas I've talked about. So although students develop understandings of science in different ways and at different rates, opportunities to learn entail that all students have chances to create deep and usable knowledge so they can apply ideas and to explain compelling phenomena, solve challenging problems, and explain more and learn more when needed. So we really need to focus on can we get kids really to explain challenging phenomena. These opportunities need to occur throughout an individual's life because learning challenging big ideas is not development inevitable, but tends upon experiences and education. You can think of some, you can think about digestion and how a third grader might explain digestion compared to a high school student, compared to a doctor. But at every level, kids can have some appropriate ideas about what happens when digestion occurs. Deep understanding only develops when individuals make sense of challenging situation or complex problems. And this, just to link back to the two sessions we talked about this morning, they're only going to make sense of those if we can actually come up with interesting scenarios. Us coming up with compelling phenomena, problems, this is critical if we're actually going to get kids to really make sense of challenging situations. Challenging situations won't go anywhere if the kid's not interested in it, right? So it's up to us to really stop to think about what's challenging for children. Some of the work that I did with Laura, and I haven't mentioned elsewhere yet, but when we create these learning progressions, when we create these three-dimensional learning progressions, they can actually serve as rulers. So once we get them validated, then in different situations, teachers can use those learning progressions to basically say, where are my kids at? and what's my next step that I have to take. That's probably one of the most powerful uses of learning progressions, but you do have to go through a very careful reliability and validity process for both your curriculum materials and your assessment tasks. So, big message: how should science instruction and assessment be designed for the 21st century? We need to design instruction and assessments with respect to these learning progressions. Big ideas and scientific practices have to develop together. I can't stress that enough. And now we have time for, I want to really thank my colleagues. A lot of this work that I presented today is both with Dr. my result of my work with Dr. Nam-Soo Shin, Pong He, and Laura Kaderis. I certainly, in my lifetime, have been handsomely funded by the National Science Foundation. And I'm going to just switch this slide. If you're really interested in the talk that I gave today, it's actually based upon an article that I just published with Nam-Soo. It's called Students' Conceptions, Conceptual Change in Learning Progression, and it's in the Handbook of Research and Science Education that was recently published in 2022. And there's some other readings that are journal-based that you can look at. And I'm just going to flip through, as you start to think of questions, I'm going to flip through, I went too far. I'm going to flip through, there we go. I wanted to just get back to this slide, and the reason why is if you go to that tiny URL, so tinyurl.com, SciCar 2024, you can download the PowerPoint. So that's in there, right? I think that will help you if I spoke too fast or if you wanted to get to any of those readings. And with that, it's time for questions. We have 15 minutes. My watch just went off. It's just a clap.
So we have 15 minutes. Yes. So I'm sure that please.
Thank you very much for your presentation. You already answered this question according to the presentation, but anyway, let me ask. As we know, cognitive constructivist learning theories distinguish between primitive and radical constructivism. So, and now my question is, where is this usable knowledge is constructed following your principles is located on this scale from primitive to radical constructivism. Is it understood? My English is very poor. So.
I have bad hearing. Did you get the question, Barbara?
Okay.
Can you just repeat it?
I mentioned that in learning cognitive constructivist learning theories, they are distinguishing between primitive constructivism and radical constructivism.
Yeah.
And so the question is, where is the meaningful knowledge constructed following your principles and so on, would be located on this scale?
Right. So this model of learning actually doesn't go into radical constructivism. It really builds on more of a slow conceptual change across time and not radical constructionism, right? So the model here is that if at an early age I can start building some appropriate conceptions of what energy is, some appropriate conceptions of what natural selection is, then I can slowly build it and becoming richer and richer across time. The notion of radical constructionism basically says that I've been running around with a misunderstanding in my mind, and I have to now change that. And so I need some new form of, I have to just restructure everything. And that's not what this model is built on. This model is built upon more of one, if we can start working with children early on and slowly build their understanding across time, we're going to make more progress.
Construction of knowledge.
But they're going to construct knowledge across time, yes.
Yes.
But not a radical reconstruction. It's a slow building of knowledge appropriately through, and the point I tried to make I think, am I out of the vision of the camera? I can't stand behind these podiums, just to let you know. Anyways, it's the slow building of knowledge across time. Of course, that takes appropriate instruction. So we need appropriate instruction. Teachers need appropriate professional learning. And then we can slowly build appropriate ideas across time. That's going to prevent a lot of the problems that we've seen in the past, where kids come to us with misunderstandings related to force, misunderstanding related to matter, misunderstandings with kids related to energy.
Okay, thank you.
Thank you very much. Do we have additional questions, please? Yari, please.
So this use of knowledge, usable knowledge, powerful knowledge is important. And when a teacher is designing a lesson, he or she should think very carefully how to support the building of usable knowledge and the networks. And then you have to combine also those scientific practices in your teaching learning situation. So my understanding is that, I hope you can correct it if it is wrong, so it is not necessary to have a kind of whole inquiry process. So it's more important that teachers are thinking that how to combine those core ideas and practices in a clever way. So it's somehow picking them together and not the whole process, I mean inquiry process. That is not so important if you are looking for usable knowledge. How you evaluate?
It's really critical if kids are really going to develop knowledge that they can use in a new situation. It's really critical that they do it in a particular context along with the practice, and then that disciplinary idea and that practice is going to develop together, right? So if you can think about, I have a slide, I didn't use it today, but I had a slide to say, just imagine if kids in 3rd grade started to develop models, which is fairly sophisticated about some big idea, and then they continue to develop models in the middle school and high school, we would have very different learners. And of course, I first used that slide before I ever even had any evidence that 3rd graders or 2nd graders could actually build models. But nowadays, we really have evidence that kids can, at the 2nd and 3rd grade level and 4th grade level, build models. More importantly, we also know, we have some really strong evidence about some other work that I've done with Barbara that shows that modeling is a critical factor in actually having kids develop, having kids achieve better in science. So having these things work together is very critical.
Please.
Thank you for excellent presentation. Let me focus for a moment on the teacher's knowledge and skills as well, because I completely agree with you that this progression-oriented model is very good. But we know that in the States, but also in Estonia and in many other countries, we are suffering from teacher shortages, which means that sometimes the teachers do not have that kind of connections between the core ideas, what you mentioned. You didn't ask the audience to reflect how many of them saw just topics when they closed their eyes and how many of them saw the connections. So that I think that it's really challenging to have that kind of instruction, because we might have not teachers who are capable for that. Do you see that now, taking the advantages of AI, maybe it is possible to learn science in a way as you described?
Good question. And you do mention a really important part of the world that we exist in right now. Not all our teachers are necessarily prepared, right? Teaching is a very, very important, critical profession. And as a society, as a world, we often don't give it its respect. And we need to we need to prepare teachers better so they develop the kind of knowledge that they're needed to do this kind of instruction. And we need to make it a profession that people want to go into. Now, can AI help education? Well, I can ask the question, can AI help doctors? The answer is absolutely correct, right? AI is being used in medical scenes all the time, trying to detect, is this really cancer or not cancer? And it's only when it's a case that's not clear cut that it goes in front of a doctor, right? And a doctor makes a choice, right? But yeah, so can AI help? The answer is probably yes, although I don't see the world of a kid sitting behind a computer by himself and getting just instructions from an AI, right? I would imagine that it'd be extremely boring. It's not how science takes place. But could AI, if I'm a teacher and I got a certain group of kids in front of me that have a certain background, that come in with certain prior experiences, can I then say to generative AI, could I say, you know, giving these learning goals, given where my kids are at, given these curriculum materials I have, how might you modify this so I can really build their knowledge further? And then perhaps generative AI can come back and give me some information about how I might work with my class. And those materials could, from a teacher's perspective, could be more educative, and it could support in helping a teacher become better, right? Just like it could support me as a doctor in making a decision, it could support me as a teacher making a decision on where I should go with my class from an instructional standpoint. But, you know, my vision of science education is not one of kids sitting behind a computer. My vision of science education is kids working together in groups, talking with each other, trying to make sense of stuff. And certainly, generative AI could support the process in giving the teacher suggestions on what she could do next. Generative AI could also support the teacher in saying, and perhaps scoring my models. Models are very complex to score. Generative or AI could certainly, not necessarily generative AI, but AI could certainly evaluate my models and say, hey, you got a group of kids back there that aren't doing too well. You want to go pay attention to them. So I can envision a world which AI and generative AI can help on, but not kids sitting behind a computer.
So it's time to thank Professor Kracjik. Thank you, Joe, for a very comprehensive and scholarly done work. There's a lot of it, and we are looking forward to listening to you many, many times more. Thank you very much.
Well, I don't know how many more times it is, but I do want to
many times.
I did not thank Mia or Yari or Rahel inviting me as part of SciCar. It's really been a great experience being part of this. I think I've been involved in at least this, I believe is my third one, or it could be my fourth one, I'm not sure. But it's been very valuable in being part of these situations. I've learned a lot, and I hope that the people who have listened to me throughout the years have learned a little bit as well.
We can't see ourselves without you. Thank you.
Mm-hmm.